So I'm going to talk about stochastic gravitational background in the DeciHertz band without paying any particular attention to any specific project or something like that. This is all general right now, it's open ground. And this is like, I think maybe if we counted that how many times this plot was shown, this is probably the 100th time we are showing this. But only thing I want to point out here is that, of course, we are trying to fill this gap here. So we need a bridge in this frequency band. And maybe, I think I thought I'll say three things here. Yeah. One thing is that there is no reason to believe that we need only one bridge here. Because even when we are doing the early warning for reliable forecasting, I think we may need actually more than one detector and perhaps 3 detectors. People will slowly come up with that idea. And there are many ideas floating around. So we may as well have 3 detectors. There is no problem. I mean, things may look very too optimistic right now, but you know, there are exponential growths in the field. So often suddenly it feels like, oh, why we are not thinking about 3? That maybe I'm high. Okay, the other part I wanted to say about the bridging part also, I hope that it also creates more bridges between different countries and collaboration. So that is another route, which is improving, but let's say it does better. One important thing I wanted to point out here is that if you see these ones, especially the Tiango, this is from the Tiango science paper, which I think is very comprehensive in terms of the science cases, even though we should work on it more, is that there is this region. You can see that these are the sort of the sensitivity curves. And this is, I think, Einstein telescope, right? Yeah. And C will also come somewhere here. There is this specific region where the DeciHertz space-based or like whatever, I mean, lunar DeciHertz detectors can work in coincidence with the ground-based detector, which effectively can give us a baseline which is 1 million kilometers long, like multiple baselines. This part is actually can be very important. So which eventually leads to, I'll come to that, exquisite source localization on the sky. And also, so now the thing is that this part, of course, you get very high source localization, very good source localization. In this part also, if you want good localization, I think multiple detectors will be necessary. And here also one important thing, I think I am just saying things which have already been done here, but just in case people missed it, like I missed it, is that, you know, when we talk about forecasting with LISA and so on, we talk about we are talking about months to years. So let's say that LISA is launched in 2035, and then you wait for a few years, that is 2040. By that time, we don't know what is going to happen here, okay? Meaning whether the Voyager, the detectors are working, whether C and others are funded and this thing. But on the other hand, in a more nearer term, there is a chance that the Voyagers are going to operate because the sites are already there. There are the vacuum tubes. At that point, if you have a detector in the DeciHertz band, if you look at this line, that this is the timeline, that how much in advance we are predicting, we are forecasting. This can be in the scale of minutes. So then, if a DeciHertz detector starts operating and ground-based detectors are already there, you start getting source localization and forecasting out of the box almost. You don't have to wait any longer. I think this is going to be one of the most important science cases for a DeciHertz detector. Okay, I think everything else is covered, and then these are the kind of so this is from the Tiango science case paper, and you can see that you can get like almost sub 0.01 square degree source localization for nearby sources, and also with this is for forecasting. This is like days before forecast you can do it, and then of course it becomes better and better. And here, with even for very large distances, you can get exquisite source localization with ground and space-based the detector. You get better than 0.01 square degree source localization for sources which are at the highest redshift possible. This is unbelievable because this can tell us how not only give a good measurement of Hubble constant, but how the Hubble parameter is varying with redshift. So this kind of things would be possible with this. Now, why did I say this? This paper which summarizes this is this Tiango paper, and it mentions everything, but it does not mention anything about the stochastic background, and that is absolutely correct. The DeciHertz detectors, even though like were proposed for the primary motivation to detect a primordial gravitational wave background, that is not the primary science case for this detector. The only forecasting and precise source localization is absolutely sufficient to propose a DeciHertz detector, and that's where we should focus on. Nevertheless, we are obsessed about that first second, what happened in the first second in the universe. And the whole aim of, I guess, humanity finally boils down to how everything started. But then this is not going to happen very soon, and may not be even in our lifetime, except for the fact that we may be able to find the signature of the primordial gravitational waves which were generated in the inflation. I'll spend one slide on that, on the cosmic microwave background B mode polarization. And these ones which are mentioned here, CMB-S4, which is a set of ground-based detectors, and LightBird, I think both of them are going to start taking data later this decade. So there is a significant chance that now I should be careful about my words, but I should still say there is an indirect effect of the primordial gravitational waves which can be measured. It is like Hall stellar binary pulsar. When we detected gravitational waves from Hall stellar binary pulsar, we said it's an indirect detection, and this is also going to be the signature of the primordial gravitational waves on cosmic microwave background B mode polarization. So it is like that detection will be kind of indirect, but the direct detection with a cluster of detector like this or some other model, I think we'll have to can take decades, and that is good because it's, as they say, that the journey is more important than destination. We have a lot of things to do. The thing is that even though we have a pretty good picture about the history of the universe, there are glaring gaps in our understanding. I mean, the two most important ones, of course, there are many others, that many measurements don't match and things like that, but two most important ones, I think, is inflation, that where the universe actually expanded many e-folds during that period. Even though it's a very short period, if you see the whole expansion history of the universe, a significant amount of expansion happened in this fraction of a second. And this part is completely put by hand. There is no direct observational evidence. It is just that if you don't include this part, you cannot explain how the perturbations were generated in the early universe, why the CMB sky looks so statistically isotropic, and things like that. And then also the dark energy. It's also 70% of the universe's dark energy. It is also put by hand, and we need to see how it evolves. And by the way, I think this is not the part of the talk. This is what the main topic is. But then a DeciHertz detector can put significant light on this part also, as I said, that especially by measuring the Hubble constant, Hubble parameter. Now, what is this inflationary stochastic background? I think most of you are familiar. Just to remind you that that suppose there was a slow roll inflation happened, that is, there was a field which is fluctuating in the universe in the vacuum. I mean, there are vacuum fluctuation, and suddenly the universe expanded, and then it generated some modes which went out of the horizon, and they did not die as it was expanding. So they got frozen because the wavelengths were larger than the horizon size. And then the universe again eventually started expanding much slowly. Those modes entered, and their amplitudes were kind of frozen at that point. So they remained. And this is, I mean, the rough mechanism how the inflationary gravitational waves are there, and they are present even right now, which we can measure. And with different CMB measurements, I think somehow the quality of maybe I'm connected to the wrong Wi-Fi, which is why I'm doing it through EduRoam. Just let me see if I can change it so that the quality on this will improve. Yeah. Okay. Okay. So with the present CMB measurements, a lot of constraints were put on the something called the tensor to scalar ratio and the primordial, the tilt of the primordial power spectrum and so on. But then there is a good chance that the tensor to scalar ratio is of the order of 0.01, which corresponds to a omega GW, if we'll come to that, of let's say of 10 to the minus 16. Now this plot is very promising, very attractive, that everyone wants to detect this inflationary gravitational background is very different bands. And at the time when this was published, we thought that I was thinking, because I was a PhD student at that time, that maybe in the next few years this will be done. So because I was a PhD student, I was not smart enough to understand that this is not going to happen so soon. And now, it has to almost 20 years, and this is still there. And this is again one of the most attractive things, as I said. Now, yesterday also you saw in Seiji Kawamura's talk that the DeciGo, the final configuration of DeciGo, may be able to detect this inflationary background. And this is one of the motivations, even though he did mention that they are working on a more optimized configuration so that this sensitivity curve could be moved little below this thing. But that is good enough, because this is 3 years correlation, you can increase the amount of correlation and so on. And once you detect, it becomes much easier to get more money to fly more satellites, and also technology will become easier. See, this is, again, these plots are not completely precise, I would say. But then let's just start with that why this DeciHertz band is important is because after you have removed all the resolvable binaries, there remains a small narrow window here where you can have you can actually probe the DeciHertz, the primordial gravitational waves directly in the DeciHertz band. There is nothing else which is there. So this sounds optimistic, but then there are many other things which are involved in the details. The thing is that this band is also not going to be absolutely clean. There will be things which will remain and so on. So, and I will spend some time on that. Okay. So just before going there. So, when we are trying to detect this kind of things, we have to worry about two things for these primordial gravitational waves. One is the sensitivity of your detector, that the detector should be able to have enough sensitivity to go below the expected signal strength. The other part is the foregrounds, and I will come to that very soon. Now, how do we, first let me just tell you what is the current, how we detect gravitational waves, the stochastic gravitational background, just one slide. So basically, if you have two detectors which are sufficiently far away, or at least they don't have any correlated noise, then there will be a signal part and the noise part. That the noise part is basically uncorrelated, and the signal part will have some correlation convolved with the antenna pattern functions, etc. And you use this correlation to detect gravitational waves. So in some sense, one detector signal is kind of acts as a noisy filter for the other detectors data. And then these are the this is a bit old plot, but anyway, so these are the kind of upper limits which are put by the LIGO-Virgo-Kagra collaboration on the stochastic background. So this is the O1, and then now with O3 we will be somewhere here and so on. And eventually, even within A plus and this kind of configuration, we may be able to detect the binary background created by the binary black hole mergers in the distant universe. So basically, this is a confusion noise that you are looking so far away that you don't know, you cannot identify individual sources. Like I can identify individual persons here, but if this room becomes extremely large and people are sitting far away, then it will look like a fuzzy background created by humans. So that is what this background is. Other than this, there are no clear upper limit on the stochastic background yet, meaning there are some limits which come from Big Bang nucleosynthesis, etc., but not like a specific upper limit like this. So what happens is that this background on of compact binary coalescences actually depend on many other astrophysical parameters, and therefore you have quite a bit of uncertainty on what would be the exact background. But this is nevertheless crucial because of the reasons which will follow a little later. Now the thing is that if you put all those parameters somehow in this in your calculation and try to estimate when you are going to detect a stochastic gravitational wave background, it sort of comes out to be few years. There is a lot of large error bars, so it could be maybe in 05, 04 we'll detect something, maybe somewhat later. But since this meeting is focused on the DeciHertz band, for the purpose of that, I think before any DeciHertz detector starts taking sensitive data, we would be able to detect the stochastic background from binaries, and that will be one of the important things. Now, what happens when the 3G detectors come? Now, one may say that, well, this stochastic background is not at all important because, you know, with 3G, we are going to detect every binary black hole in the universe. Yeah, I mean, not really. Yes, it is true that that part is true that you will detect probably all the binary black holes in the universe, but not the binary neutron stars. Okay, so there is we have to wait quite a bit. So, sorry, with at least with Voyager. So what happens here is that when you have Voyager here, you detect all the binary black holes in the universe essentially. Voyager is here, but in terms of the neutron star merger, Voyager is kind of here. Okay, so you see that this whole binary neutron star mergers are going to create a stochastic background for Voyager. With 3G, which may come in again probably to 2040s, this you may be able to detect all of them, but that is much later. But by 2035 or 2030s, we may be able to detect the stochastic background created by this. But then the question is that why is it important? Now, why is it important can be explained with these plots. So this was again slightly old, but this was done by Pablo Rosado. You see that there are many astrophysical backgrounds which are predicted by so for different kind of considerations of binary white dwarfs, neutron stars, etc. And these are plotted here. Now this part is only the stochastic background, and this says that at that time there was still the hope for BBO, which is not there anymore. But then there are DeciGo and things like that. But you see, there is quite a strong background still present here. Okay, and also if you see, so the thing is, the main idea, the crucial point here would be to actually estimate this background. The reason is that I'll just show it. Okay, one more thing before I move to that even if you don't consider the resolvable one, so this is only for the unresolved one, that is the pure stochastic background before removing overlapping signals. But if you include everything, which is not a bad thing actually, you just include everything, then you get a better estimate for these lines which are passing through. Okay. The idea is that, so this is a recent plot. See, here is the primordial background. Okay. And if you think that the DeciHertz band is completely empty, it may not be the case. I mean, cosmic strings is just one of the thing. You can see that this line is coming here. This is for stellar mass CBCs. This is essentially orders of magnitude high even now then. What you could do is that if you remove all the sources, all the resolvable ones here, it may come somewhere here. Nevertheless, it is going to be overlapping with the primordial background. Now, if suppose you say, that is okay, but where is that? That's okay, because we can only consider this part of the frequency spectrum, then you are essentially reducing your sensitivity by a factor of 2, which obviously you don't want to do, because then you are losing the sensitivity to detect. So essentially the point is that all these signals have to be very, very precisely estimated. And how do you do that? The thing is that I think those who are familiar with CMB, you would know that, the primary cosmic microwave background is in 100 hertz to 200 hertz, this sort of band. But then CMB spans CMB detectors span an entire range, like it starts from 30 hertz, 44 gigahertz, and so on. On this side, there is 857, 544, and things like that. And you would think, like, why are we going there? The thing is that where CMB is most significant, the other foregrounds are subdominant. You cannot make a precise measurement of those foreground components in that band. So the measurements has to be done in those bands where those components are most significant. And which is why the best way to estimate the stochastic background created by these binaries is by observing through the ground-based detectors. And this is in the true spirits of multiband observations, that you have to combine. I think to detect the primordial background, you have to put everything on the table so that we detect it. Otherwise, something like this can happen. You know what happened with the CMB detections, that people thought they have detected the primordial background, and it turned out that it is just the polarization created by galactic dust. And obviously, you don't want any such situation. Okay, now moving on. So the binary part was quite significantly covered, and as you can see in this plot, this is the binaries are kind of covered, and then there are quite a bit of more or less accurate estimates for that. What is so far not covered is the spinning neutron stars. Now, this is the kind of the distribution of spinning neutron stars in our galaxy. Okay, and then you can extend it to the whole universal population of the universe and things like that. What happens is that, okay, let me tell you something. Okay, I'm going to talk about a paper which was written by Sanjeev Dhurandhar and others to see whether the Virgo cluster, which has a very large population of millisecond pulsars, can be detected or not. And they used somewhat, so they used this radiometer algorithm where, if you have two detectors and you want to find the strength of the signal which is coming from a certain direction, you start correlating the signal and use Earth rotation synthesis imaging to find the strength of the signal in that direction. When you put those things and you come up with some sort of effective strain, power spectral density for the signal, you get something like this. So these are the sort of effective strain, and this is for very high ellipticity. In practice, you would not be able to detect it in this band. That's not a good thing. The thing is that, so this is the plot which Deepali made yesterday. So you see, these are the power spectral densities for different ellipticities for the pulsars. Okay. Now, this is the primordial background. And here is the DeciHertz band, essentially. And you can see that for 10 to the power minus 16 omega, this barely touches one of those optimistic DeciHertz band sensitivities. Optimistic, but it's possible to do, but so that's not a big problem. Now, the problem here is that these things again are going to extend this. We could extend it here. Okay, so this is the primarily it overlaps in this region here. Okay, now if you want to estimate all these the total contribution of the primordial background in these detectors, there will be a significant effect of these backgrounds which can come in this detectors band. One way would be to cut off the whole bandwidth of the detector, that you say that you believe in some model where only a small part is going to contribute. The other part would be, and even then you have to be careful that what exactly, so this is from a certain distribution. If the distribution is different, you may end up getting some other kind of tilt. I think Arunovo's plot we could not show, but that shows actually quite a bit of strong signal up here, not exactly here. But the point which I'm trying to say is that at the end of the day, we have to understand these foreground components which are leaking in the primordial gravitational wave background band, like the band where we are trying to make the measurement, is going to become very important. And we have to basically take LISA's observations to find what is the distribution of heavy black holes, which can tell us what is the black hole formation scenario and so on, whether it is like hierarchical merger scenario, etc., or there is a seed black hole, those things. These models will then can be combined with LIGO's observation on the completely and entire frequency band. And then finally, we can get the proper residuals in this band where the primordial gravitational wave is. And then finally, we will be able to claim, even if we detect a primordial gravitational wave background in a detector like a DeciHertz band, we will not be able to claim a detection simply because of these foreground issues like the CMB. And only when we combine all of these, we may be able to confidently say that, yes, there is a detection. And when you get all those things, so we wrote some papers earlier that, when there are multiple components of gravitational wave backgrounds, let's say, of different power law indices, then you can do this kind of things. Like, again, this is kind of motivated by CMB people, what they used to do. Now this has become very common there, but this was done a long time ago. That how you can produce these corner plots to make an sort of unbiased estimate. And also recently, there were papers which Jishnu and Dipali, they were involved to see how you can make component separation maps with this. Now, the thing is that this may be slightly, so these things would be useful for the present detectors after the first detection is made, let's say in the few years' time. But then these things all can be stretched to the DeciHertz band for more precise estimates of different things. Okay, I think I will stop here with the summary. So basically, I mean, this conference already makes this point that DeciHertz band promises exciting science. I mean, I will just highlight again that the major science case, everything is interesting, of course. I mean, what interests me the most is probably not even going to be included in that science case document. But on the other hand, just forecasting and localization of binary mergers closer to the event, not like months to years in advance, makes a very strong case for a DeciHertz detector, and we should go for it, and probably not just one, probably more than one. And detecting the primordial stochastic background is going to be one of the biggest achievement probably of humanity at some point, because we will know what exactly happened in the first second. But then again, foreground removal will be a fundamental issue, assuming that we eventually reach the required noise sensitivity to go below that the background which is predicted at that time. And finally, these things may look a bit futuristic, but the detection of astrophysical stochastic background can happen essentially in the next few years. And then this results that whatever is detected, which will tell us how much is the high redshift contribution of these compact binary coalescences, and which then again can be extrapolated to the lower frequencies. And also the methods which are being developed should help us in the analysis for the DeciHertz band as well. Okay, thank you.
Thank you, Sanjit. Are there questions? We can take a couple of questions. Yes, up there.
Thank you for the very nice talk. I'm just trying to understand something fundamental. So you had that, you had one slide where you showed that you effectively need multiple gravitational wave detectors to get a cross correlation to get a stochastic background, right?
I mean, many of these had the same idea, but multiple.
No, this you cross-correlated S1 with S2. Effectively, you said one detector acts as a filter for the other one. So should I take it then that you would require multiple DeciHertz detectors to get a stochastic background, or am I misunderstanding?
Perfect. Yeah, I love this question because then chair has to give me more time now. The thing is that the thing is that here I showed you this part, this plot. So I mentioned that, there is this part for certain configuration. This actually does not apply to LGWA, but it does apply to Tiango, that there is an overlap between the ground-based detectors and a DeciHertz detector. So here you can directly use that possibility. But if you truly want to do science in the DeciHertz band, okay, I don't think you should rely on this. You should have at least 2 DeciHertz detectors.
So just to quick follow up. So would it help if we had multiple GWAs on the moon?
I asked that in the first day, so it is not very clear that when that's going to happen. Like I think what Ian has said is that it can only be in the polar regions. So maybe I think the South Pole and the North Pole would be just 2 possibilities. But let's say that you have one LGWA, okay? That sits right here. Suppose you have one LGWA and one DeciHertz detector, right? For this band, you will correlate, let's say, whatever, Tiango or something with LGWA. This band, you will correlate Tiango and any ground-based, let's say, whatever is there at some point, maybe Voyager or Einstein telescope. So that should be, I think, enough. I mean, we may have to develop some techniques to how to kind of combine 2 detectors data from different these things. But eventually, we in this analysis, we assume that every frequency band is independent. So in that spirit, I think it may go through. But we have to do some more analysis on that.
Yeah, the space detector would have to be close to Earth to correlate with LGWA. But in any case, so LGWA correlate with the SIGO, for example, which is like somewhere else.
I think varying distance. We have to see because so I don't know how the radio astronomers actually do these things, but when they have this array of detectors and they basically scan this, what is called this UV plane sort of. So suppose the detector distance was varying, so maybe they will not be like a spiral track, but it will be like some curved track. Maybe that can still work out. But I think these are nice problems.
No, that should be fine. But yeah, I think the overlap reduction function is like 0 essentially between the SIGO and LGWA just because of distance, because there are like millions of kilometers between them. Oh,
you mean that for the isotropic part?
Yes.
That is right. For the right. So I forgot to mention one thing for the astrophysical parameter estimation. So the hotspot paper I mentioned is actually for a localized gravitational waves. It is not for the isotropic one. And we were thinking that for isotropic one, we should do it. Now, suppose you don't know the isotropic background exactly, you cannot measure it. But by combining these clusters and integrating over this thing, you may be able to get the isotropic background tail in that insensitive band. I mean, these are like, nobody has worked it out. I mean, this is. Yeah.
Is there another question?
There was
somewhere. Oh, yeah. Yep.
Hello. Yeah. So can you go to the slide, the last plot that you had?
Yeah, this one.
This one. Yeah, I'm assuming that the straight line that you are showing here, is it the primordial graph?
This is the primordial one. Yeah.
So, and the curve with which it is intersecting the PSD, it seems to me that it's DeciGo.
Correct.
So the PSD of LGW lies well, I mean, above that PSD. So if suppose we have, even if we have multiple LGWs, LGW detectors, even in that case, we'll be able to detect these primordial gravitational waves, or will be able to put just constraints on these.
The detection of primordial gravitational wave background with LGW will be quite difficult. But suppose you have one detector, one space-based, or I don't know how to say it, like one Tiango-like detector in space and one LGW, then even if the relative sensitivity differs, the final sensitivity depends on the geometric mean of the sensitivities. So you may be able to do a little better.
Okay. Thank you.
Okay, thank you again, Sanjit. I think we have to go into the break.